One, two. Welcome to Online Precalculus. Today's section is 5-1, Verifying Trigonometric Identities. And this section only has one objective. All right, so we're going to use fundamental trigonometric identities to verify other identities. Okay, this section is probably one of my favorites, right? It's a lot of fun because what we're going to be doing is we're going to be taking the different identities that we'll look at in a second, and we're going to be using them to manipulate other equations to get the two sides to be equal. Okay, we're like solving a puzzle. All right. And so in chapter 4, we use the unit circle to establish these relationships among different trigonometric functions based on what the sine was equal to in terms of the radius and the two sides, cosine, and we made something that looks like this. So these are all the fundamental trigonometric identities. We have the reciprocal, the quotient, the Pythagorean, and the even odd. And while these might seem like a lot, these are the start because there are many more. So we'll start with the reciprocal identities, but these are also the most common. So the reciprocal identities say the sine is the 1 over the cosecant, the cosine is 1 over the secant, and the tangent is 1 over the cotangent. And my reciprocal identities also work for cosecant is 1 over the sine, secant is 1 over the cosine, and cotangent is 1 over the tangent. My quotient identities are for tangent and cotangent, and they're sine over cosine for tangent. Cotangent is cosine over sine. Typically, we're going to use these two way more than we're going to use the reciprocal identities of tangent and cotangent. Okay, typically when we're working with verifying fundamental identities, the most common technique and the one that works the most often is to change everything into similar terms so that I can cancel stuff, okay? And the most basic stuff we have is usually in terms of sines and cosines. Cosecant can turn into a sine, secant can turn into a cosine, tangent and cotangent can turn into these ratios of sine and cosine, okay? So that is my basic strategy to be able to simplify these things. The Pythagorean identities is sine squared plus cosine squared is equal to 1. 1 plus the tangent squared is equal to the secant squared, and 1 plus the cotangent squared is equal to the cosecant squared. Now, these are great the way they are, and that's a good way to remember them. You also can rearrange them. You could also subtract the sine squared from both sides, and now you have a new identity that says cosine squared is equal to 1 minus the sine squared. Okay, so that is a thing as well. Okay, so you can rearrange all three of these Pythagorean identities into three different things. The basic one, you can subtract the sine from both sides, you can subtract the cosine from both sides. All right, the key to remembering them is sine and cosine go together. Tangent and secant go together, and cotangent, cosecant go together. They both have the same letter. Tangent, secant, those are the opposite letters. So sine and cosine, those are the two basics. They go together. Tangent goes with the one that's not the same letter. Cotangent, cosecant, right, same letter. Finally, the even odd identities are the ones we'll probably use the least, but you can see that sine, cosecant, tangent, and cotangent are all odd, because a negative inside the function gives you the negative of the function. Cosine and secant are both even. All right, so do you have to remember all these? It's probably a good idea, right? So the more you use these, the less you'll have to rely on a formula sheet, but it is a good idea to maybe take a quick screenshot of this. Where's my eraser? There we go. Take a quick screenshot of this and use it as you're trying to work out these problems. All right, so let's see what we're actually going to do with these. So think geometry proofs without saying the actual thing that you're doing. So it's not a formal 2-column proof like geometry, but we're going to do the same way. We're going to be changing one side of the equation. We're going to be manipulating one side of the equation in order to get the thing to equal the other thing, whatever the thing happens to be. So the fundamental trigonometric identities are used to establish other relationships among trigonometric functions. To verify an identity, we show that one side of the identity can be simplified so that it's identical to the other side. Each side of the equation is manipulated independently. This is important, okay? It's manipulated independently of the other side. So what that means is this is not an equation, right? You cannot cross the equal sign to help. You can't add things to both sides. You can't multiply things to both sides. We're trying to show that this side, the left side, is equal to the other side. Okay, so you don't want to cross the equal sign. It's a good idea to start with the side that is more complicated and try to simplify it, as opposed to starting with the side that is less complicated and try to make it look like the other side. Usually it's a better idea to just simplify everything as much as possible, and hopefully when you're done, the two sides will be equal to each other. If you substitute one or more fundamental identities on the more complicated side, you'll often be able to rewrite and form identical to the other side. No one method or technique can be used to verify every identity. That's why this is so fun, because again, it is like a puzzle. Okay, you're going to develop different techniques. I'm going to show you a bunch of different techniques in this section that you can use to get yourself started. But basically, it comes down to, recognizing different things that you can do inside of each identity and trying to manipulate the two equations to get them to be equal to each other. The most basic technique and the one that will work the most often is rewriting the more complicated side so it only contains sines and cosines. So let's start. Okay, so here's the way this works. We have two terms. Secant cotangent is equal to cosecant. I'm not going to do this every time, but remember that the secant is equal to 1 over the cosine, and the cotangent is equal to the cosine over the sine. Okay, so with those two identities right there, and we should know what the cosecant is. With those two identities right there, we can manipulate this left-hand side, the more complicated side, to make it look like the right-hand side. So my goal is to first change everything on the left-hand side to sines and cosines. So I'm going to change the secant to 1 over the cosine. The cotangent is going to be the cosine over the sine, and equal to the cosecant. Now that we have similar terms like cosine and we have multiplication, right? So we have this fraction times this fraction, we can now cancel those out. So 1 over the sine is equal to the cosecant, and the definition of cosecant is 1 over the sine. So this has been verified. I now have shown that this identity, secant cotangent, is equal to cosecant. Now, this identity is not something that you should try to remember. Okay, yeah, it works, but I mean, it's just easier to show that it's equal as opposed to trying to just remember all the different variants. And there's too many. There's an infinite number of ways that you could set up the left-hand side here to be equal to cosecant. All right, let's try a got a problem. Let's try the next one, a checkpoint. Okay, so similar problem. The first problem and the second problem here are always going to be very similar. So cosecant is 1 over the sine. Tangent is the sine over the cosine. And just one thing for notation is just remember that trig functions have a variable, right? They have some sort of x or theta or something. So you can't just write sine, cosine, right? You do need to put a variable. Okay, secant of x, sines cancel. 1 over cosine is equal to the secant, and the definition of secant is 1 over the cosine. So this is verified. Okay, so again, I talked a little bit about this before. What's the difference between solving an equation and verifying that an equation is identity? When you solve an equation, you work both sides at once, adding, subtracting, multiplying, and dividing the sides by the same expression. You verify an identity by working independently of the other side. So solving an equation, you could see, first step you distributed, then you put the like terms together, and then the next thing you did was subtract 6 from both sides to isolate the variable. Okay, and then you got an answer. That's not what verifying an identity is. Verifying an identity is you don't cross the equal sign. So you work only with the left side, you manipulate only one side, and at the end you say these two things are equal to each other. Right? You're not getting an answer, you're not getting a number. You're showing that the two sides are indeed the same. Why can't you verify an identity by adding something to both sides? Is because if you do, right, you're saying that these two sides are equal to each other, right? That's the way equations work. Is the left side is equal to the right side, so it lets you cross the equal sign as long as you do the same thing to both sides. Here we're trying to show, in verifying an identity, we're trying to show that the left and the right side are equal to each other. So you can't assume it's true. You do not know that it's true until after you are done verifying the identity. Okay, let's try another one. Okay, so again, easiest way to get started, and the one that usually works the most often, is to change everything to sines and cosines. Well, sine is already a sine. Tangent is the sine over the cosine, plus the cosine is equal to the secant. Whoops. Okay, so here we have two terms. We're trying to show it's equal to one term. Probably we're going to have to put these two terms together. So that is the sine squared over the cosine plus a cosine. Well, I still have two terms. I'm going to have to put them together. The way you put two fractions together is to make a common denominator. So my common denominator would be cosine. This doesn't change. All right, now if I'm going to multiply the bottom by cosine, I have to multiply the top by cosine as well. Okay, now what I can do is combine these to one fraction. And hopefully recognize that the sine squared plus the cosine squares is an identity. And when you add them together, you get 1. And 1 over the cosine, by definition, is the secant. So this is verified identity. Again, let's break it down again. What did we do? We changed tangent to sines and cosines. Then we multiplied the terms together. Then we combined the fractions, used a Pythagorean identity in order to make them equal to 1. Let's try it again. Again, the process here is going to be very similar. In fact, almost exactly the same. So the cosine times cotangent is cosine over the sine plus the sine is equal to the cosecant. That turns into cosine squared over the sine plus a sine. Again, what do I see? I see two terms. So I'm going to combine these into one term with a common denominator. And so that change stays the same. This one, right, I have to multiply the top and the bottom. So that changed to sine squared. Cosine squared plus sine squared is 1. And 1 over the sine, whoops, is the cosecant. Okay, so we really only used a couple of identities here. We used the reciprocal identities. We used the Pythagorean identity right there. So we only really used a reciprocal identity there. So 3 things total in order to get this function to look, or for the left side to equal to the right side. So some identities are verified using factoring to simplify a trigonometric expression. So now when we look at this function, I can't change everything to sines and cosines because they're already sines and cosines. So the only thing I can do is notice, well, hey, look, there's a cosine in the first term, a cosine in the second term. I can factor it out. 1 is left over there, and sine squared is left over there. Oops. So now looking at this, 1 minus sine squared is an identity. Remember that my Pythagorean identity says that sine squared plus cosine squared is equal to 1. When I subtract sine squared from both sides, I get that 1 minus sine squared is equal to cosine squared. And then just like 2 variables, right? A cosine to the first power times a cosine to the second power, we add the exponent together and we get that this is cosine to the third power. Very similar here for our checkpoint problem. Factor out the sine. 1 minus the cosine squared. Okay. 1 minus the cosine squared is sine squared. And multiplying these two together gives me sine to the third power. And now that is verified. Often, there is more than one technique that can be used to verify an identity. So again, it's like solving a puzzle, right? What can you do to get the 2 sides to be equal to each other? Let's look at this problem right here, and let's do it 2 different ways. So in the first way, let's manipulate only the left-hand side. So 1 plus the sine of theta over the cosine of theta, whoops, is equal to the secant plus the tangent. Okay, so here I have a fraction. Hopefully you remember that if we have 2 things over the same denominator, right, we can split those into 2 fractions. We can split those into 2 fractions, kind of like that. So we're going to split this. I don't know what's going on with this new program for this. 1 over cosine is plus the sine over the cosine is equal to the secant plus the tangent. And 1 over the cosine is the secant. Sine over cosine is the tangent. So that works. But that's not the only way to do it. Let's do it a different way. So 1 plus the sine of theta over the cosine is equal to the secant plus the tangent. Now, you don't have to work with the left-hand side, right? We've been doing that all this time, but you don't have to. You could work with the right-hand side. As long as you don't cross the equal sign, you can do anything you want to either side separately. So 1 plus the sine over the cosine secant is 1 over the cosine plus tangent is the sine over the cosine. And now they both have the common denominator of cosine, so I can add them together. So it just turns into, whoops, right, 1 plus sine. So 1 plus over the cosine. And this is verified. So on the left side here, we verified this by changing that side. And over here, we changed around that side, the right side. It doesn't matter. Whichever you see, whatever you want to do. I would say that the left side looks more complicated than the right side. So I might do the, the expression on the left side over here, as opposed to the other one on the right side. But it doesn't matter. Let's try it again, okay? And I'm not going to do both this time. Let's just focus on the left side of the equation here. Let's split it into two fractions. So 1 over the sine of theta plus the cosine over the sine of theta. And then I'm pretty much done already, right? Because 1 over the sine is the cosecant, and cosine over the sine is the cotangent. Okay, so this is verified. And again, if you wanted to start with the right-hand side, you could do that as well. So, how do you verify identities which sums or difference of fractions in which trigonometric expressions appear on one side? Like this problem, okay? You're gonna have to combine these two fractions. Notice that we have two expressions equal to one thing on the right. So you're gonna have to combine these. And the way you combine two fractions is to find the least common denominator. Well, these two denominators have nothing in common. So the least common denominator is just the two denominators multiplied together. Whoops. Okay, so I just multiply the denominators together. That means this first fraction, I have to multiply the numerator by what's missing from the denominator. And in the second fraction, I have to take the numerator and multiply by what's missing in the denominator. Okay? And this is equal to 2 secant of x. Okay, so let's simplify this numerator a bit. So that's cosine squared. I'm going to have to FOIL these two together. So that turns into 1 plus a sine and another sine. So that's 2 sine x plus the last term is sine squared x. And that's over 1 plus the sine of x times the cosine. Now, you could distribute these two things together, but based on experience here, you're going to get to realize that don't cancel things that mix sines and, or don't distribute things that mix sines and cosines together, because you're going to want a chance to cancel them out with something later. The reason why I had to multiply everything together up top was because I had two terms. So this is similar to the technique that we use when we are working with rational expressions. And we're trying to cancel things. So sometimes you want to distribute them out. Sometimes you want to leave them in a factored form. Okay, and you'll get sort of the hang of that. All right, cosine squared and sine squared, when you add those two together, you get 1. And so now the numerator is 1 plus 1 gives me 2 plus 2 sine x over 1 plus the sine of x times the cosine of x. And again, what's our goal here? Keep looking at our goal, 2 secant x. I can factor out a 2 there, and I'm left with 1 plus the sine of x over, and look at this, 1 plus the sine of x times the cosine of x. These two cancel, and I'm left with 2 over the cosine of x. 2 over the cosine of x is the same thing as 2 times 1 over the cosine of x, and 1 over the cosine of x is the secant. So 2 times the secant. Ran out of room there. Okay. So again, what was my steps here? Find a common denominator, multiply the numerators by what's missing from the common denominator, simplify the numerator, and cancel. And let's try one that's very, very similar. Try to get some more room here. Common denominator is 1 plus the cosine times the sine. And the numerator now is sine squared plus 1 times 2 cosine plus cosine squared. Remember, because you're multiplying 1 plus cosine times 1 plus cosine, you must FOIL them together and don't lose the middle term. Okay? Sine squared, cosine squared, add together to give you 1. So now we have 2 plus 2 cosine over 1 plus the cosine times the sine. And that's equal to 2 cosecant. Okay, factor out the 1, or sorry, factor out the 2, and you get 1 plus the cosine. This is fun. Over 1 plus the cosine times the sine. Cancel, cancel. So now we have 2 over the sine of x is equal to, right? We didn't lose my right-hand side here. I just ran out of room in the last slide. And 2 over the sine is 2 cosecant. Notice we never crossed the equal sign. We never needed to manipulate the right-hand side. I could have, if I wanted to change that to a sine, I could change that to 2 over sine, and I could have met the answer right down there. Sometimes identities are verified using a technique that may remind you of rationalizing the denominator. So when you look at this problem here, it's really hard to figure out where to go. You can't split this into two fractions. That's not the way denominators work. You can do this 1 over sine plus minus cosine over sine. I could have said, well, that's the cosecant minus the cotangent, but that's not getting me there, okay? So this is actually a good problem to demonstrate a very important point when it comes to trying to verify an identity. If you are working through the problem and you are getting to a place where you don't know what to do next, there's nothing else you can do, there is one thing you should do, and that is start over. Okay? So again, there's more than one right way to solve things. You can do many different techniques, but if you work yourself into a hole like I did right there, you really do need to just go back to the beginning and try a different, don't do the same thing over again. You're going to get to the same spot you were before. Do something different. Okay. So what I notice here is that because I have a binomial in the denominator on the left-hand side, what I can do is I am allowed, I can't multiply both sides by 1 plus cosine. I can't do that. Okay. But what I can do is I can take only the left-hand side and I can multiply by anything I want, as long as it's the same thing on the top and the same thing on the bottom, right? I'm not crossing the equal sign. Okay. So what I want to do is multiply the top and the bottom by 1 minus cosine. Okay. And this gives me something, it makes something really nice happen, because this is not an identity. 1 plus cosine you can't change into anything. But when I multiply by its conjugate, I get 1 minus the cosine squared, which is an identity. Okay, the top, let's leave it factored for now, because again, remember what I said before, is that you really don't want to mix up terms with sines and cosines if you can help it. And watch what happens. 1 minus the cosine squared is the sine squared. And now we can cancel one of these with this one, and we're left with 1 minus the cosine squared over the sine. And that is now a verified identity. Okay, oops. So again, what do I do here is I multiply the left side by the conjugate of the denominator, because a single cosine is not going to be able to change into anything, but a cosine squared has a chance to if you have a Pythagorean identity. So 1 minus the cosine squared can make something cancel out for you. Let's try it again. And right away, I'm just going to know that, okay, I see this denominator. Okay, I see that it doesn't have anything squared in it. I want to do something with the left-hand side, so I'm going to multiply by the conjugate. Again, nothing to do on the right-hand side. Okay, I could split this up if I wanted to, but this works out pretty nicely without having to do that. So the numerator is the cosine times 1 minus the sine, and the denominator is 1 minus the sine squared. And my 1 minus sine squared turns into cosine squared. So 1 minus, no, whoops, sorry. 1 minus sine squared is cosine squared, and that cancels with one of those. And so now I have 1 minus the sine over the cosine, which is where I want to go. Okay, so we were able to verify this using this technique that is similar to rationalizing the denominator. Okay. Here's one where we have to use our even odd identities. Okay, so let's start this by changing everything to sines and cosines. So tangent is the sine over the cosine. This negative with sign could come out front because it's odd, and that changes to a plus sign over 1 plus the cosine of x. Before I start going crazy with multiplying by conjugates of the denominators, I really should clean up the numerator up here. Okay, so I really should try to make this into one fraction, and then let's see what happens after that. So in order to do that, I'm going to need a common denominator. So that's the sine over the cosine plus the sine times the cosine over a cosine. And all of that is still over 1 plus the cosine. I'm going to need more room here, so we're gonna just skip the. We're going to just go over to the right here. These now have a common denominator, so that is the sine plus the sine times the cosine over the cosine over 1 plus the cosine. Okay, so, and that's all equal to the tangent. Probably thinking, how am I going to get this just to a tangent? All right, so remember that when you have a fraction over a fraction, you multiply by the reciprocal. So let's go up here. So we have the sine of x plus the sine times the cosine over the cosine times the reciprocal of the bottom. Whoops, 1 plus cosine. And now, notice I can factor something out. So factor out a sine, and that leaves me with 1 plus the cosine over the cosine times 1 over 1 plus the cosine. And now those two cancel, and I'm left with the sine over the cosine, which is equal to tangent. Okay, so what did I do here? I fixed that. I changed tangents to sines and cosines, and then I just used algebra. Okay, I just manipulated this expression, right? Made the fractions have a common denominator, put them together, fraction divided by a fraction, I multiply by the reciprocal, factor out the sign, cancel, and see what you're left with. Okay, so a little bit more complicated, but still something that we're able to work with. Same idea for this one. Cosecant is odd as well, so that negative can just come out in front. Secant is 1 over the cosine plus, minus the cosecant, so that's minus the 1 over the sine. And on the bottom, right, we're changing everything to sines and cosines. Secant is 1 over the cosine times cosecant is 1 over the sine. Okay, so the bottom is multiplication. That's pretty easy to put together. The top is, and where are we trying to go? We're trying to go to sine minus the cosine. Okay, so at least this one's a little bit different. The top is subtraction, so we're going to need a common denominator. The common denominator is cosine times the sine. So numerator becomes sine minus the cosine. Denominator becomes 1 over the cosine times the sine. And 2 to divide a fraction by a fraction, we multiply by the reciprocal, and this works out very nicely. So it's just the sine of x minus the cosine of x over the cosine times the sine times the reciprocal of the bottom, which is the cosine times the sine over 1. Those two cancel, And where am I trying to go? The sine minus the cosine. And that's all that's left. So the sine minus the cosine of x is equal to the sine minus the cosine. And that is now verified. Okay, so fractions over fractions, combine them, multiply by the reciprocal of the denominator. All of these problems we pretty much identified by working only with one side. You don't have to do that. If you wanted to, you can work each side independently. Don't cross the equal sign. And you could show that both sides are the same thing. Okay. Important though, not to cross the equal sign. Okay. So let's see how we could do that with this. All right, so what do I see here? I see two fractions. I see some stuff over on the left. So let's go with these two fractions. I'm going to need a common denominator to put them together. So that's going to be 1 plus the cosine, 1 plus the cosine of theta times 1 minus the cosine of theta. This numerator turns into 1 minus the cosine of theta plus 1 plus the cosine of theta. And that's going to be equal to, let's just leave it blank there for a second, okay? Because we're going to change that around as well. But let's just stick with the left-hand side a little bit. 2, we got 1 and 1. Cosine, negative cosine, positive cosine cancel each other out. Over, multiplying these two together is 1 minus cosine squared. And that is going to be 1 minus cosine, or 1 minus cosine squared is equal to something. I could keep this going a little bit, but let's see what happens when I mess with the right-hand side a little bit. I notice that I can factor out a 2. Okay, and that gives me 1 plus the cotangent squared of theta. And the cotangent squared, oh, that's an identity. Let's do this a little bit differently. Sorry. Let's go 2 plus 2 times the cosine, over the sine. The other thing I was doing would probably be faster, but I just wanted to make a quick point here. Common denominator here, so that would be sine squared. So this is going to be 2 plus 2 cosine squared over the sine squared. To have a common denominator, it has to be sine squared. So we have 2 sine squared plus 2 cosine squared over the sine squared. And again, I could have done this a little bit more efficiently. Let's factor out the 2, and we get that the sine squared plus the cosine squared over the sine squared. And I'm going to jump back over here because I know that 1 minus cosine squared is sine squared, and sine squared plus cosine squared goes away because it's 1, and now I have 2 over sine squared for both sides. Okay, so as long as they meet somewhere in the middle, you could cancel it. Or you could say that the two sides are identities. Now let's try that again. Let's be a little bit more efficient and try to work with maybe just the left side a little bit. All right, so again, my common denominator is going to be 1 plus the sine of theta times 1 minus the sine of theta, which makes the numerator 1 minus the sine plus 1 plus the sine. Okay, so what are we trying to do? Let's just factor out the 2, and we get 1 plus the tangent squared, theta, not x. Okay. 1 and 1 is 2. Signs cancel, positive and negative. Factor these, we get 1 minus the sine squared, which is 2 over the cosine squared. And 2 over the cosine squared is 2 times the secant squared, right? If 1 over the cosine is secant, 1 over cosine squared is secant squared. And let's even meet this a little bit in the identity, because this is an identity. It's a Pythagorean identity, and it's equal to 2 times the secant squared. So, and I changed everything to an x, even though it should be theta. Sorry. Okay. But again, we'd still use the same technique of working with the left side and the right side, but you don't have to, right? You could have said, okay, secant squared, I can change that to 1 plus the tangent squared. And you could have worked it from there. Okay? But again, whatever works for you, and then you could have distributed it, and we could have gotten right back to there. But again, whatever you see, however you see to help you verify these problems, do whatever you need to do. Okay, so let's take a quick look here at a few different methods to verify this identity. So there's more than one correct way to solve a puzzle, right? That's what I said at the beginning. So one method may be shorter and more efficient than another. As long as you get to the answer, it's okay. Try to get to the point where you can be more familiar with these types of problems, and you can see the most efficient way to verify each identity. For instance, this problem. One approach, and we're going to look at a couple of approaches. One approach is that a Pythagorean identity, 1 plus cotangent squared is equal to cosecant. So you can change all those cosecants to 1 plus cotangent squared, giving you something like this. So cosecant changes to 1 plus cotangent squared. And so now the 1's can cancel out, and you have cotangent over cosecant, which is cotangent is cosine over sine. Cosecant is 1 over sine squared. Sine squares cancel, and you get what you were trying to get, which was cosine squared. Okay, not terrible, but maybe there's an easier way. Okay, so by splitting this into 2 fractions, same problem, okay, by splitting this into 2 fractions, cosecant over cosecant and 1 over cosecant, you now have 1 minus sine squared, which is equal to cosine squared. So a little bit better than messing around with this fraction over fraction, having to multiply by the reciprocal. Okay. Another way to do it is to change everything to sines and cosines. It works. However, it's much longer. Okay. So the idea here is to start to recognize some things that could happen, to try it out. If you don't get to where you're going, changing everything to sines and cosines is a good place to fall back to. Okay. So again, changing everything to sines and cosines might be the way that you wanted to start if you're not used to these problems. But as you start doing them more and more, you realize that there might be more efficient ways to solve them, especially if you see something with a binomial over a monomial. You usually always want to split it into two fractions. And the more you do this, the more identities you prove, the more confident and efficient you will become. And practice is the only way to get better at this. But here are a few guidelines to help you. Okay? So what do you want to do to try to do these problems? So first, work with each side of the equation independently. Very important. Start with a more complicated side and transform it in a step-by-step fashion until it looks like the other side. Good, good way to start. Complicated, make it easier. I analyze the identity and look for opportunities to apply some of the fundamental identities, especially a trigonometric identity. A Pythagorean identity. Usually those are the ones that can make these problems a little bit simpler. So rewrite it. First step, try using one of the techniques. Rewrite it in terms of sines and cosines. Factor out common factors. Separate single term quotients into two terms. Combine fractional expressions using least common denominators. Multiply a numerator and denominator by a binomial factor that appears on the other side of the identity. The last one is the most important, and I said this before. Don't be afraid to stop and start over again if you're not getting anywhere. Creative puzzle solvers know that strategies leading to dead ends provide good problem-solving ideas later. Can be a little bit frustrating. What I will say is that if you go through the problem, and I said this before, if you go through the problem and you're not getting anywhere and you want to start over, that's fine. Just don't do the same thing. If you put everything in terms of sines and cosines, maybe do something like this, right? Multiply by a binomial factor, or make a common denominator, or use a Pythagorean identity, or do something different, right? Single term quotient. That's kind of what the point of this problem was, is that maybe you did it this way, maybe you wanted to do it this way, okay? So again, look for something different to do. All right, let's try a little more complicated problems. This one's shouldn't be too terrible. Immediately when I look at this, I want to remember that I have two things and I have one thing on the right hand side. So let's put these two fractions together. And I'm going to do that with a common denominator. So here's where it gets a little bit tricky. So the common denominator here is the sine times the cosine. Okay, that makes this cosine times the sine plus the cosine minus the sine times the cosine minus the sine. Okay, so now I don't really see much to do in the bottom here. So let's just distribute everything in the top and see what happens. So this is cosine times the sine plus the cosine squared minus the cosine, or minus the sine times the cosine plus the sine squared over the sine times the cosine. Cosine sine cosine. Multiplication is commutative. Doesn't matter what order I write the terms in, x, y, y, x. All right, they are opposites, can cancel each other out. Cosine and sine cancel to be a positive 1. So we have 1 over the sine times 1 over the cosine. I don't have to separate them like that. I could have left them together. 1 over the sine is the cosecant, and 1 over the cosine is the secant, which is where I wanted to go. Okay, so I just put this problem in there that even though the numerator gets fairly complicated, it really does simplify into something nice and simple. Have one more, okay? And I included this problem at the end just to remind you of something, that even the identities, even the formulas that we use way back in the beginning of the year always come back eventually. And this one happens to be the difference of perfect cubes. And the way you factor the difference of perfect cubes is using SOAP. So we have same sign, opposite sign, always positive. So hopefully you remember that, or else this problem would have been very difficult. If you did remember that, this problem is very simple. So this is the difference of two perfect cubes. It factors into the sign, same sign, sine squared, opposite sign, multiply them together, sine, cosine, always positive, over the sine minus the cosine. Those two cancel out. Sine squared plus cosine squared equals 1. And I'm left with 1 plus the sine and the cosine, which is where I want to go. Okay, and that was 5-1, verifying trigonometric identities.